You. Thank you for remembering to do that, Tish. Sorry, that was my job. Yeah, to help make collaborations easier, help make the science better, and kind of exchange information. And so I know there are a lot of online seminars that have been going on over the last couple of years, but we did think this was the best way to bring together what is a group of researchers that are pretty spread out globally and internationally. And so we won't be having these very frequently, but we are interested in trying to keep some momentum going in these discussions, and we'd be very welcome to hear different ideas you have about how to use this time. We were very interested as a working group to combine both some science presentations, but also to hear about something that we're going to hear about today, which is logistics of different cruises, examples of things that worked well and otherwise. So I am very grateful to have Patricia Yager, Anna Wåhlin, and shortly Rob Hall here. They're going to talk about, oh, Rob, there you are. Very good. Thanks for joining. So they're going to talk about the cruise that happened earlier this year as part of the ITGC, which is the International Thwaites Glacier Collaboration. This cruise hosted 3 different projects, Thor, which we will not hear about today, but Tarzan, which Anna, Wåhlin, and Rob are going to talk about, and there are others here on the call who are part of that, including Karen Haywood. And then an add-on to the ITGC was a project that was funded through NSF Office of Polar Programs, led by Tish Yager and others, called Artemis. And so the plan today is to have just a brief overview of those projects. We're going to do 3 presentations of about 15 minutes each. I'm going to try to keep the speakers to time because I want to make sure that we have time for discussion and questions at the end. I will be keeping an eye on the chat, so please put your questions there during the talk, and we can even have some discussion via chat, especially for those who aren't presenting at the time. Okay, so thanks again. Rob, are you okay to start?
Yeah, that should be fine.
Excellent, thanks very much.
Want me to share screen now?
Please.
Okey-dokey. Okay, can you see all that?
Yeah, that looks good. And just, I'll keep an eye on the time for you, Rob, but if you sort of finish by about 20 past, that would be great.
Yeah, not a problem. Can you see my pointer as well?
Yes, we can.
Yeah, excellent. Okay, so yeah, so I'm Rob Hall, and I was leading the Tarzan component of the MVP 2202 cruise. This is, as Andy stated, very much a kind of a summary of the Tarzan-based observations that we did. I'm going to kind of do a fly-by visit to all of the different systems we used, with the exception of the Hugin, because Anna's going to go. This is work that's been contributed by lots of people, and it's very much work in progress. So, why is that not changing? There we go. Okay, so MVP 2202 was early on this year. As Andy said, it was a combination of Tarzan, Artemis, and Thor. The original plan, of course, was to go to Thwaites Glacier. That's the focal point of the ITGC collaborative group of projects. But we hit thick sea ice around Thwaites Glacier, and we decided pretty early on that we wouldn't make it into that polynya and get to the glacier. So we had a backup plan. The Tarzan backup plan has always been Dodson, and so we decided as a group that we'd spend a good chunk of our time working in and around the Dodson region, kind of see what the ice developed like. As it happened, the ice just got worse. And so once we kind of had our fill of Dodson, we also did some operations at Gets A and B. Also, on our way in and out, we did quite a lot of work in the open polynya, particularly associated with the Artemis project. This is just a quick summary of the ship tracks in front of the ice shelves. Doesn't kind of show the open linear work or the shelf edge work, but shows the density of observations and ship tracks that we did there. And a shout out here to Callum Rollo, who was a PhD student with me and Karen, who developed this excellent online data kind of ship track and data display system that's currently still live, and we're going to try and make it a more permanent feature. Okay, right. So different systems we were using. Start off, we had, as a physical oceanographer that I am, our workhorse system on the Rosette was our standard seabird system, and we had upwards and downward looking 300 kilohertz ADCPs from the UK marine equipment pool. We did a lot of CTD casts over the course of the cruise, over 250. A whole bunch of those were in a 24-hour yo-yo time series that was roundabout here at Dodson. And the ADCP, lowered ADCP, worked really, really well. We got great data from that. We only had a few, 2 or 3 casts out of that 200 or more where we had any issues with our lowered ADCP. So that system worked really nice. And these are some figures from Tiago, who unfortunately can't be here today because he's on holiday. Just summarizing some of the data we've got off of this system. On the right-hand side, in the arrows are colored by the temperature, and the size of the vectors is the speed and direction of the flow from the lowered ADCP. And we see up near just near the ice draft, we can really see the outflow of Dodson here. And we're starting to see a bit of inflow here on the other side of Dodson. That's up at just beneath the ice draft. If we go towards the bottom, we're really seeing more of that that warm inflow, much nearer the seabed. The other big ship-based, and of course the great thing about the lowered ADCP is that it gives you the full depth structure. So what we have now here is just a section along the Dodson ice face. We've got conservative temperature with the ice draft in purple, and this is a section from the lowered ADCP data, so we can really see some lovely fine structure of the outflow and the inflow in front, in and out of Dodson. The other major ship, and of course, the other thing we did, which was a part of Tarzan, but also very closely associated with Artemis, is we had noble gas sampling being taken by Laura Glasgow from University of Rhode Island. She did a huge effort and collected something like 700 odd samples from the CTD from all over Dodson and Getz and out in the Plinia, way more than can be actually analysed. So we're going to have to do some cherry picking of which ones to process for looking at things like hydrothermal activity, water mass circulation, and so forth. So this should be work starting soon when the samples arrive. So CTD Rosette, lowered ADCP are standard ship-based systems. The other useful ship-based system we had was a vertical microstructure profiler, the VMP 2000. So this is, for those of you who know about these types of systems, this is a tethered microstructure profiler, and is good for about, with the amount of cable we had, it's good for about 1,500 meters, which is more than deep enough for this work in front of Dodson and Getz. We did almost 250 profiles in a variety of sections. We did a lot of work in and around the inflow and outflow of Getz, trying to characterize the turbulent environment in these constrained inflow and outflow regions. We see there's a huge amount of variability, both spatially, both geospatially. We can really see that the highest mixing rates are quite near the ice front in the outflow, but in inflow, we get high mixing rates quite far away from the ice face. Looking at the depth structure again, we're really seeing that the highest mixing rates are near bed at the inflow, where we're seeing the strongest flow in the low density data. And of course, we have some high mixing rates near the surface, which are usually to do with wind mixing. As this is talks very much about, or this group is very much about kind of practicalities. One thing you may notice that a lot of these lines are a bit slightly wonky angles. This was because on the Palmer, we were forever battling the wind and the thrusters, and we had to do a lot of on the fly thinking about directions that we could safely do these microstructure sections in. So each of these cases we were running basically into the wind, and so we would kind of come up with various plans, and as the wind developed we would kind of alter them during our kind of period of EMPing. But it worked well. We got good coverage over those regions. Time. Okay. Okay, we did a lot of autonomous ocean glider work. We deployed about 6 gliders all over the Plinia. So some of them we launched in the open water, out near the top end of the Plinia, and in the middle. We launched others right near the ice face. And in total, we got about 1,300 dives in 150 glide days. So that's a huge density of glider data. They were all equipped with different sensors, standard temperature, salinity, dissolved oxygen, chlorophyll, but also some new developmental sensors like nitrate, pH, turbulent microstructure. And this is a talk in itself, but we have a postdoc working under the Artemis project, Yishi, who will be heading up a lot of this glider data in the future. From a kind of practical point of view, running gliders with this amount of icebergs around is really tricky. We spent a lot of time chasing gliders that had got not stuck in ice, but were coming up under icebergs or damaging sensors. I broke about 8 or 9 microstructure probes just by crashing gliders into bits of sea ice. So it wasn't a simple task, but we got a lot of data from these autonomous systems, and that was the real value of the Tarzan project. It was ship-based observations, but we'd used a lot of autonomous systems as well. The gliders, which I've mentioned here, then 2 Paraday UVs, the Huygen, which Anna will talk about in a minute, and then also the AutoSub long range, which is the UK NERC Mars long range AUV. It's a very different beast from Anna's Huygen. I'm sure we'll give an overview on that, but the AutoSub long range is a much smaller vehicle designed for longer endurance with a lighter sensor load. I kind of think of it as kind of halfway between a glider and a big kind of Huygen type AUV. We weren't really using it to its full endurance capabilities. We were running missions up to 2 days, with the longest missions we ran, but it does have the capability of running for weeks or even months at a time if you have good enough navigation. The limiting factor we had was poor bathymetry and therefore poor navigation. We started off small, did test missions away from the ice, and then we started to run ALR under the ice on these straight lines running north-south straight into the under the ice shelf, tracking the bottom. It was mostly running at about 100 meters from the bottom to get its best navigation. And we had it equipped with the standard hydrography, chlorophyll, backscatter, but also we get current measurements from the ADCPs and DBLs that are used for navigation, and also turbulent microstructure from a microstructure system in the ALR's nose. Something also to note is we ran the ALR very, very close to a mooring that was put out by one of the other ITGC projects, MELT. They were there simultaneously, and they did a through ice mooring through Dodson, and we ran it within a kilometre or so of that mooring. So that's going to be a really nice data from Harrison, looking at that long-term mooring data set with our kind of spatial ALR data set. Again, a lot of challenges with ALR under ice. That's probably a talk in itself. We did lose it for about 2 days, but she turned up a long way from where we left it. So there you go. And the final autonomous system, it's not really an autonomous vehicle, but it's certainly autonomous, is we had a large seal tagging effort from the University of St Andrews. We deployed a total of 21 tags that came from both Tarzan and Artemis projects. Because we couldn't get anywhere near the Edwards Islands, which is where the open beaches are, we had to do all of our tagging from a small boat on seals that were on ice floes. So it was a big effort. We had to put a lot of time into it, but we got a very efficient system running, and we got all of our tags out. Mostly they were Weddalls, as you'd expect on the ice, but one small, well, relatively small elephant seal turned up on an ice floe, so they tagged that one as well. And so most of our tagging took place in this region here, just north of Bear Peninsula. But you can see that we've got a great spread of data now. The seals have really moved out all around the Plinia, moving in front of Dodson and all the other ice shelves. We've got about 5,000 or so CTD profiles already, and these will be collecting data all the way through to the fall, kind of November time. I'm going to just finish up here. Work in progress, future plans. We're currently going through a QC process for most of our data sets, some further than others. The CTD, lowered HTTP and BMP is probably the furthest ahead. The seal tagging is all coming back in real time. There'll be a final QCing and packaging for distribution once we get to the fall. Anna will talk about the Hugin. ALR, we need to think carefully about where and how fast the platform was going, particularly with things like trying to work out microstructure data from an ALR and a glider. You really need to be careful about working out vehicle speeds, otherwise you'll get a vastly wrong dissipation rate. So a lot of work in progress with those more complex systems, but our more standard CTD, BMPs and glider data is all coming on nicely. That's 20 past. I think I will finish there.
That's great, Rob. Thanks very much. There's already one question for you in the chat, and I actually may add one as well. But in the interest of time, let's move on to Anna's talk, and then we'll make sure that we have time for some discussion at the end as well. That was a great start, Rob. Thanks very much.
There we go. Can you see me flipping through these?
Yes, we can. Yep.
Great.
Good.
Thank you. So yeah, thanks for that great introduction to the overall cruise. And I'm going to tell you a little bit more details about what we did with the Hugin AUV. And my name is Anna Wåhlin, and I'm a professor at the University of Gothenburg in Sweden. And together with me, we had Li Ling, who is a PhD student at Stockholm, and Anders Sjövall and Mark Simons, who are technicians working with this system. And if you want to read more about our AUV, there is a link here. So as Rob was talking about, it's quite a big difference when you have big AUVs like RAN. The big AUVs are faster. They are moving by propeller. And since they are faster, they can survey larger areas in shorter time. And they are also stable platforms. They are heavier and more stable, and they are designed for good acoustic surveying. And the traditional use of them has been multi-beam and side-scan sonar, and now it's also moving towards ADCPs and so on. Of course, we have many sensors, so there's also all the chemistry, physics sensors, CTDs, etc. But they were designed once upon a time for the acoustic sensors. The drawback of the large AVs is that it's a big operation on board. They come in 30 or 40 foot containers, and they are quite expensive to maintain and operate, not to mention the investment. And in my opinion, the best usage is if you can use them for unique research tasks to get data that only large AVs can get. One example is under the ice shelves of Antarctica, and another example is to go close to the seabed so that you get very high resolution bathymetry, for example. And this is a picture of the AUV. So in our AUV nowadays comes in a 40-foot container, and you have inside something that's called a LARS. It means launch and recovery system. And it's quite convenient. It's big and heavy, but once you get it on the ship, everything is there. So that was quite good before. And then, of course, if you want to, it's not easy to find space on deck of a 40-foot container, or this is how we used to operate it with a 25-foot container, but then you have to wheel it out so that it actually occupies a larger deck space all in all. And that means essentially that you can't there's other operations that are ruled out. So you should really, it's a big investment, and it occupies ship time and ship space. So you should really think carefully before bringing it on board. Here is just a picture showing how you fasten the container on deck. This is not easy either on an icebreaker, because usually you're not allowed to weld on icebreakers because they come with heating below deck. So you can't weld on that, then you break the heating pipes. And yeah, in our case, we had to manufacture special plates because the container was so heavy. And a bit more about our AUV. This movie is from tests that we did in Sweden the winter before. We took it to the Amundsen Sea. It's depth rated to 3,000 meters, and you can run missions up to 300 kilometers. And the cruise speed is between 2 and 6 knots. This model of AUV has very good navigation. It's better than most other AUVs on the market. And the movie shows how it came up after a 10-hour mission in one of the Swedish fjords under the ice there. So we were very happy with that test. And all in all, at the moment, we have 31 sensors on it. It's upward and downward looking multi-beams, temperature, salinity, oxygen, nitrate, CO2. And we also have capacity to take water samples. And here is an example of the resolution that you get on the bathymetry when you are at normal operation. So the image you see now is what you see from a high quality ship multi-beam. It's about 600 meters deep. So the ship is on the surface and the distance to bottom is 600 meters. And then you get this resolution. But with an AUV, you can get much closer to the seabed, and then you get the resolution looking like this. So that means that we can get much finer detail of the seabed, and that means in turn that you can figure out what happened the last time this area, for example, was under ice, and as the ice moved and as the ice moved away from this region, as it let go. And here is the same part of the same area with something called a side scan sonar, which has even higher resolution, but you don't get values of depth from the side scan. You get an image instead, an acoustic image of the seabed. They are good in combination. Yeah, so we are, as Rob explained, we have been looking at the thwaites, what goes on there in the ocean, and we had two quite large. We had the Wåhlin, which is about twice the size here on the left, but we also had the Boatimac boatface, which is slightly smaller, but I think that was the first time that they are still quite large AUVs, and we operated them both underneath an ice shelf at the same time, and I think that has not been done before. So it was very exciting. Here is a picture of the Hugin being launched. So it comes out when it's time to launch it. You press a button, and then the doors open, and slide goes out, and then it folds down into the ocean. And here it is before it folds down. It worked really nicely. This was the first time we operated this launch and recovery system, and we were very happy with the results. And as Rob said, we are still processing data, but we do know that we have a lot of data. So we got hydrography and dissolved oxygen and chlorophyll, optical backscatter, currents and water samples, and multibeam from the seabed and upward-looking multibeam from the ice, and much more. All in all, we had 14 missions with the Hugin AUV, and the total distance was 1,732 kilometers, of which over 1,000 were underneath the ice. And we also got water samples under the ice here. And this map shows we focused on dots on ice shelf. That's where we did most of our missions. And as you see, we have tried to make these lawnmower patterns. They are good for making maps, both of the seabed and of the ice. And this little small pattern down here, that is at the melt mooring site. So we also have a good map of the melt mooring site. We do get already, we know from the technical, how the AV behave technically. We got so it uses something called a DVL when it navigates. It's ADCP essentially that has bottom track so that you get dead reckoning, and then it combines that with an inertial navigation unit. And when you plan missions, you have to be careful so that you stay close enough. So there's one looking up and one looking down. And when you go near the ice, you want to be close enough so that this ADCP reaches the ice, because otherwise you can get lost. And then you also have to decide for yourself what the safe distance is, how close do you want to get to the ice and not get. And then you need to plan the mission so that you are somewhere in between the DVL reach and the safe distance. And that's fine. We have an overall view of the thickness of the ice from satellites, but the problem is when it changes abruptly, and it did. We noticed, we didn't know before, but we learned that there are several big cracks in dots on ice shelf that you see on the bottom. And when you enter into an area where you have a crack like that, you can potentially get into problem. So this is the planned path for the AUV at the planned depth, and you're here nicely away from you have a safe distance to the ice and so on. And then you can enter below a crack and nothing much happens. And if the ice becomes thicker than you think it would have been, it adjusts down. So in this case, you suddenly get a bit thicker than the safe distance. Then the AUV senses that and adjusts down. And now if you have adjusted down like that, and enter into an area where you have a crack. So you have the adjusted plan here, and the AUV knows it's at higher, deeper down than it's supposed to be. and then you suddenly have a crack on top of it. Then it will try to adjust upwards. Again, back to the original plan, and then you can get into trouble, because then these cracks are very abrupt. Some of them are vertical walls, essentially. And then you can be in a situation where you don't have time to adjust down again, to avoid the wall at the other side of the crack. So we didn't think about this particularly before we ran these missions, but we noticed that we were lucky in a few times, and then we realized that it's very important to either know exactly where the cracks are, or to have a rough idea of the thickness of the ice, because it's very, very easy to get into this situation. And if you don't plan well, to have the original plan must be at a good depth. If you put that too shallow, then you will also get into trouble whenever you encounter a crack. And I believe the big autosub has been in situations like this under Pine Island. So just a little snapshot of our data. So this is on the right here, we have a map of the ice thickness as seen from underneath. So this is a multi-beam map taken by the multi-beam. The black line shows the AV path, and the colors show the ice draft. So that is the pressure of the ice surface. And we were very happy with the upward-looking multi-beam. It's the first time that we have been managing to operate it like this, with lawnmower pattern and focusing on getting maps. And we have a very high resolution. It depends on how close to the ice you are, but we have down to 10 centimeter resolution of these maps.
Just quickly, where is the direction of the ice shelf face, and where would be the direction towards the continent?
Out here is open ocean.
I see.
And then it goes there. And these are cracks, the cracks that we encountered. Yeah. You can see some of them here.
Thank you.
And we learned much. There were many processing steps and bugs. The software is not designed for looking upwards. And I don't think anyone has operated an upward-looking EM 2040 before. So we discovered many errors. It's easy to go wrong here, but in the end, we managed to convert this correctly. And we also had mounted a new long-range ADCP that was looking upwards, and we got some good first estimates of the ice draft that we used to plan the later missions where we went closer to the ice. But we have still not managed to process the velocity data properly from it. We think we have some really nice velocity data also from that ADCP that we haven't managed to convert yet, but there's a student that will work with that in fall, hopefully. So we have to do that work together with RDI and Kongsberg. And this is an example from, this part here is in the east side of the ice shelf that we have 4 or 5 maps like that of different. And this map here is from the west side. So this is where you have an outflow of meltwater enriched meltwater going out. And here, so what you see here is chlorophyll concentration from the fluorescence sensor that we have on board. And I thought it was quite striking how sharp the boundaries are between the water masses.
Anna, would you be able to finish up in just 1 or 2 minutes so that Tish has time as well?
Yep.
Great.
So this high fluorescence, we think, comes from high biological production in the open water just outside the ice shelf cavity. And we noticed that also by eye when we were with the ship close by there. The water was brown, and we noticed many things growing on the ice. So it's probably that water that has made an excursion underneath the ice. And you see also these sharp boundaries in dissolved oxygen and salinity and temperature and so on. Yeah, just this was our plan A, and as Rob said, we couldn't get in there because of sea ice. So we are hoping that we can have more expeditions. This concept seems to work quite nicely, and hopefully we can get it on around in quite close, maybe next year and maybe in 2 years. And I'm also hoping that maybe we can have a new US and or British expedition to finish up what we didn't manage to do this year. Thank you very much. Sorry if I took too long.
No, that was perfect, Anna. Thanks very much. Again, if people have questions for Anna, please put them in the chat, and maybe Rob and Anna can have a look at the comments that are in there right now, and we'll shift over to Tish.
Hey, hello everyone. I'm happy to be here. Thanks, Andy, for hosting this great webinar. So I'm here to tell you a little bit about Artemis, which is accelerating Thwaites ecosystem impacts on the Southern Ocean. Artemis was a project funded through OPP-NERC collaboration. It's it's an opportunity where NSF and NERC were working together, co-funding some collaborative work. So this project includes myself, Rob Sherrill, Sharon Stammerjohn, Patricia Medeiros, Pierre St. Laurent, Jess Fitzsimmons, and Mark Johnson from the US, and then Karen Haywood, Rob Hall, who you've just heard from, Lars Bohm, and Bastian Schwest, again, kind of taking advantage of the Tarzan cruise plan to add some biogeochemistry and ecosystem components. So you've probably seen this figure if you've thought about the Amundsen Sea at all, which most of you have. Maybe what you haven't noticed though is this plankton bloom sitting here offshore of the ice shelf. This is a very productive algal bloom in the middle of what we would otherwise call a high nutrient, low chlorophyll zone. And the reason this plankton bloom is there is because there seems to be an iron source at the melting ice shelf. So we have an iron fertilization associated with a buoyant melt plume coming from the melting ice shelf. The polynya is there because of the iron, but also because of marginal ice zone stability. This effect of seasonal sea ice melting, creating a fresher, warmer surface layer where we see the highest chlorophyll taking off in the polynya as the polynya opens up and the marginal ice zone provides stability for light to the phytoplankton. A few years ago, I guess 10 years or more now, we showed that this system has the highest biomass and some of the highest productivity in all of Antarctica. From 1 year to the next, we showed that it was a very large CO2 sink, on average 10 times the Southern Ocean average. And so it's a really important CO2 sink for the region. And if it's climate sensitive, that's what we were interested in exploring further. It also has an incredibly rich ecosystem. This ecosystem is based on Phaeocystis primarily, but also sea ice algae, lots of krill, lots of small fish, penguins, of course, and whales. A really rich benthos, it turns out, lots of large fish, and then the seals, which have been mentioned as well as the birds. So really, really inspired by the ecosystem here. It's not just the physics, it's not just sea level rise. And some of us are so intrigued by the diversity here that we'd like to explore potentially marine protected area status for this ecosystem. So if you're interested in that, please let me know. The melt and the bloom, however, are not perfectly correlated. If you increase the melt, the bloom doesn't necessarily follow. So this high variability in the bloom is not explained by high variability in the meltwater. So something else is going on. It's more complicated. So we set out a few years ago with Pierre St. Laurent and other modelers to help understand the productivity of this ecosystem as it related to the meltwater flux. And this model is a really well validated ROMS model from, you can see papers on it in 2017 and 2019, making predictions, which is what we went to follow on those predictions and test those predictions during Artemis. And many of you have seen this model. It has this warm, deep water flowing towards the glaciers, triggering the melt. It also has glacial meltwater at 150 meters flowing along as this coastal current. And then finally, the really interesting, probably iron-rich waters coming out as modified, meltwater modified CDW nearest to the ice shelf. And so this buoyancy-driven overturning circulation seems to be a pivotal part of this system. We put together this story, we call it the iron conveyor belt hypothesis, which suggests that this iron-rich modified circumpolar deep water is moving on shore, having iron added to it as it interacts with the sediments, going underneath the ice and then coming out as this meltwater modified CDW rich in iron, which is iron not just from the glacier and the basal ice and potentially subglacial meltwater, but mostly from the sediments and the MCDW itself. There's also and that triggers this bloom, that triggers the CO2 and sequestration. This iron-rich coastal current is also probably very important. It's not just the Dotson outflow triggering this bloom, but water coming from the Thwaites and Pine Island upstream, potentially even the Bellingshausen Sea, and then going downstream, fueling blooms further to the west. So really interesting system. Again, this was our hypothesis going on the ship, testing these predictions, characterizing these processes leading to the iron and carbon fluxes presently and in the future. I'll tell you about the future goals in just a little bit. One of the future scenarios is what happens when the sea ice melts. We know that the sea ice is declining. We're curious to know whether that would turn off the CO uptake and the bloom. So we went down there and joined Tarzan. Tarzan, you've probably seen this figure from ITGC. Tarzan is the Ice Ocean Atmosphere Interaction Group. And we kind of fit between them and some of the modeling groups. Thor also joined us on this cruise, which turned out to be really great for Artemis because it gave us access to the benthos. This is the team that went to sea. We had 4 early career scientists, Hilda Oliver, Lisa Herbert, Janelle Steffen, and Giovanna Utsumi with us. Rob's already told you, we focused on the CTD and we had our own trace metal CTD in addition to the conventional. We also, Artemis brought an extra glider. Rob mentioned the one that has the nitrate sensors, so we helped bring that along. We also helped bring along a few extra seal tags that had biogeochemical sensors on it. Rob didn't show you this. This is from Callum's map showing you sort of our entry in and what the sea ice looked like. This is why we went to Dodson, obviously. These were the stations that Artemis focused on. We had 23 CTD pairs, 3 additional underway transects using Rob Sherrill's tow fish, which collects a trace metal clean sample away from the ship while you're underway. We also were able, thanks to Thor, collect 17 sediment cores and overlying water samples. We also collaborated with Anna and got 7 sets of Hugin under ice samples, which I believe are the first under ice water samples collected by an IUV. We also had continuous underway data from the ship. The samples were running a long list of biogeochemical parameters, oxygen 18, of course, nutrients, carbonate, bacteria, particulate dissolved, isotope, colloidal, and ligand iron. And then at relevant steps, we tried to characterize the bloom. This was not a Polynya cruise, but we collected as much as we could to characterize the status of the bloom. So we have some pigments, organic matter characterization, bacterial DNA, etc. So the questions that Artemis was really trying to focus on was characterizing the iron fluxes and the organic matter and the CO2 and the community. Coming out of this outflow, that was the primary interest. And as Rob showed you, well, this is the outflow predicted in the model. This is Dotson outflow. And I wanted to show you this just to give you a sense of what does the outflow area look like. This is the very pocked, kind of worn out looking with a swoop compared to the Dodson ice shelf further to the east. So we definitely saw an impacted melting ice shelf front there at the Western Dodson ice. looking a lot like images from the Pine Island just a few years ago. This is the TS plot for the Dodson outflow water, and what you can see is this very classic MCDW mixing along the Gade line with the meltwater. Not much winter water in that outflow. You can see a little bit of the Antarctic surface water coming here, but we were able to, all these black dots are water samples that were collected by the Artemis team to characterize that outflow biogeochemically. Rob showed you this figure. I believe we did several transects across the Dodson ice shelf, characterizing with the shipboard ADCP as well as the CTD's lowered ADCP, really seeing this deep eastern inflow and this very strong western outflow. Also on this plot, though, I wanted to point out this very strong westward coastal current flowing right there across the center. It kind of comes in and kisses the ice shelf and then moves away. You don't really see it very strongly to the far east, a little bit to the west, but it's most strongly right there in the middle area. So we sampled the deep water, these stations coming in to the Polynya along the about 500-meter contour, trying to see whether iron was getting picked up along the way. We know we have some data that the iron at the ice shelf on the inflow is a little bit higher than the iron out here. So the iron hypothesis is that it's picking up iron along the way as it interacts with the sediments. Lots of samples there. We also, as I mentioned, collaborated with Thor. They had 11 megacores, and then we had a few monocores attached to the CTD that collected sediment, and one casting core that we sampled from to really get a handle on the flux of iron out of the sediments into that overlaying water. That was really exciting that we got that. We also collaborated, as I mentioned, with Anna, collecting these water samplers that were on the Hugin, collecting under cavity or within cavity water samples to see if there's anything in that water, how it differs from the outflow and from the inflow. We also were really interested in this coastal current, as I mentioned, characterizing the iron as it's coming around from the Pine Island in particular, and the Thwaites in particular. It was the closest we got to Thwaites was this area here. We call it the Eastern Notch. The sea ice was really thick and lots of impenetrable areas here. We tried several times to kind of get over to the Thwaites, and there was no way the captain was going in there. We did get to about here, though, and could sample that coastal current upstream from the Polynya area itself. And this is just a profile to show you sort of the classic 3-layer ocean depth profile from the Polynya area. And then this is what it looked like in the Eastern Notch, showing really highly heat and melt impacted upper layers. We also found the warmest water of all in that deepest notch. This is the CTD, again, a TS plot of all the stations. We, again, had 23 different stations, 2 casts each, and 12 depths at least along each profile. And the green areas are the Polynya areas, showing the really well-developed winter water. The red is that really interesting Eastern Notch station, showing very meltwater modified CDW. The gold are those sort of intermediate stations on the edges, sort of interacting halfway potentially between the outflow stations and the Polynya stations. We're still trying to understand those intermediate stations. And then, as I mentioned, I showed you before, the purple outflow stations showing really right along the Gade line. The brown is the Getz. So when we did go further to the west and sample the Getz, you can see that the winter water end member is completely different. CDW seems to be very similar, but maybe not. We're still exploring the role of the Getz. So what does the future hold? Future work, this is the modeling work that we will do once we've validated the updated model with the Artemis data. But the idea is to use the model to explore what happens if you change the glacial melt rate, you change the coastal ice scape, and you change the sea ice, and look at these effects as we go towards the future. What does the future hold for this ecosystem? Again, wondering whether the bloom will be sustained as climate change takes its toll. If you're interested in this work, Alison Chinchar did a CNN climate story on Artemis early May. You can take a look at that dateline if you're interested. I just wanted to end with this reminder that if you're not a member of our Amundsen and Bellingshausen Sector Regional Working Group, you can go to this website, or you can Google ABS RWG SOOS and you'll find this site. You can join the working group here, and you can keep track of all of the products and events and news on this website. And thanks to everybody who contributed to the data I just presented, and thank you.
Awesome. Thanks very much, Tish. And thanks again to Rob and Anna. We've got about a good 5 to 10 minutes for discussion. So there are a few questions in the chat that I can get to, but let me just open this up. People can either, I think at this point, just unmute themselves. And if you have a question or a comment, feel free to add it.
Shall I answer the first question in the chat?
Yeah, we can jump in there. So
Okay.
Can you see the one there from Stephen Ackley?
Yeah, so the question is, can you use the ALR ADCP to improve the bathymetry? We can, but it's only on, 2 or 3 lines. The biggest resource is Anna's Hugin data. Anna's got a lot of super high res under ice bathymetry that kind of makes the ALR bathymetry pale in by comparison. But the ALR does go further. So if you want to know exactly how bad, say, bed machine is compared to reality along that line, yeah, we can show you. And as for the second question from you, Andy,
Yeah.
we haven't really looked at the optical scatter yet. We'd have to look at optical scatter on the CCD rosette. The VMP wasn't equipped with, I know you can get like a microperimetry or something on a VMP, but I've never used one of those. It was just a standard setup. So we'd have to look at the CCD data, but we had a whole range. We had several different optical instruments down there so that we could relate AUV data sets to CTD data sets. So we've got a bunch of stuff we could look at to see if we were getting suspended sediment down there.
Great. And then my last question was, you showed that beautiful meltwater section across the face of Dotson.
Mm-hmm.
But this, and maybe because it went by a little bit quickly, I didn't see it just right. But it looked to have this interesting structure where you had multiple layers of enhanced meltwater.
Mm-hmm.
I know it's early days, but I didn't know if you had any thoughts about where that multiple layer structure is coming from.
I'm going to pass that over to Tiago when he comes back from holiday.
So maybe then to follow up, I mean, actually those two questions are paired a little bit, because I will mention that Peter Sheehan, who you know, Rob, who's at UEA and working with Karen, has been looking at the Bellingshausen Sea, and we see meltwater cores, say, at different density levels, and they do actually have different backscatter signatures to them, which we are trying to think through at the moment. And so be curious as to whether that is a feature you see elsewhere. And
I mean, one data set that we really need to pull together is all the optical data from the gliders and the CTDs, because one of the things we did was made sure we had the same spec, same frequency wet labs on the CTD rosette as we had on some of the gliders, so that we will be comparing apples with apples when it comes to integrating those data sets.
Unfortunately, it's a little bit early, I think, to answer. It's very interesting, this data, and we are just seeing it now for the first time. We haven't had much time to think what it means for the physics, unfortunately.
of course.
And the great news is the 018 samples, which we took quite a few of, as you can imagine, about 1,200, I think, have just arrived at Rutgers. So we'll start to get some of that data very soon, I hope. And the 018 should be really helpful.
Let me ask like a larger, bigger picture question then, and maybe others can chime in. So Anna, you mentioned the desire or the hope to get back to Thwaites because you didn't get in on this cruise. Maybe everyone just very briefly could talk about any things you would do differently if you were to run a similar program in front of Thwaites. Are there ways that you can sort of combine these data sets, even if you were collecting data at Thwaites in a different year? What would the goals be if you were able to go back?
Should I go first?
Sure.
Yeah. So I think to repeat what we did here, it would be marvelous if we could get into Thwaites and repeat. The difference, Thwaites has more openings, so it's not such a simple system. There is at least 3 ice shelf fronts that would be nice to cover. So maybe we can't do everything, but split it out instead. But otherwise, I think repeat just what we have managed to do here.
I didn't get that question, Andy. It was all broken up.
Yeah, sorry about that. Bigger picture question was if you were able to go back to Thwaites in the future, next year and in future years, would you do anything differently? Thoughts about thinking about the connectivity between what's happening in front of Thwaites and what's happening in front of Dotson?
I mean, one thing from a practical point of view is, even when, my understanding is, and I'm not an expert on the region, but even when the Plinia opens up in front of Thwaites, it doesn't open up to the same extent as it does in front of Dodson. And we managed to do a much more extensive glider survey at Dodson than I think we'd have ever managed to do at Thwaites, because there's just not enough open water. So I think we'd have to think more carefully about what we do with the gliders. That's for sure. For the ALR, I think our plan was to try and get in to the Amigos moorings, which were through ice moorings for the Tarzan project, from a couple of different locations. We were going to try and get in from the east and the west and get the ALR near them. And that was the kind of first order priority of the cruise, but of course didn't happen. Although ironically, we were supposed to have an Amigos mooring on Dodson, but they couldn't get to Dodson to put the Amigos mooring out 3 years ago. So there you go.
All right, thanks, Rob. Just before we go to Stephen, Tish, did you want to add anything there?
I mean, I think Artemis benefited from the Dodson work. We're very curious. According to the model, more than half the iron that comes into the Plinia is coming from the Thwaites and Pine Island system. So we would have spent more time sort of testing that idea. Absolutely. So yeah, we're really curious to see what the data from those few eastern stations give us, and that would then justify potentially going up more into the Thwaites and Pine Island area.
Great. And let's take one more question, Stephen, if you want to ask that.
Thanks. Great talks, everybody. Thank you. Nice to see some old acquaintances and friends. My question is that you mentioned a couple of times the sea ice melt, and I'm wondering how you're going to get at that. Just mention in passing, we had a couple of data buoys in that area, and it seems that the sea ice melt is actually taking place from the bottom on this, because as the ice opens up, you get incoming sunlight into the open water areas, and this causes a lot of warming. And so I think you've seen from most of the sea ice pictures there that the surface cover is pretty much intact, but we are seeing a considerable amount of bottom melt, and from the two ice mass balance buoys that we saw in that area. So I think it's something to consider. The other comment, I guess it's more of a comment on this, is that a lot of the ice is really transported out of that area before it melts. So And I think I haven't looked at it very closely, but this year was actually a very low year for sea ice in that area, and you actually had the Paulina opening out to the open ocean in front of the Dotson and Getz. Is that correct?
We still had some sea ice to get through when we came home, but it was certainly mostly open there. Not quite just north of Dotson, but certainly to the west of Dotson.
Yeah, but very ironically very heavy in the thwaites.
Right.
Yeah.
Right.
Yeah, it's a very complex picture in that area.
Yeah. So those are great points, Steve. And yeah, I would encourage my team to help work with you and see what some of these future sea ice scenarios may be that we want to test in the model. For the phytoplankton bloom, we played around a little bit with it, and it's a lot of sort of when does the open water happen relative to when is there enough sunlight for the phytoplankton to bloom, so that timing of the opening versus the bloom. And then also what's the wind doing, how deep are those sort of, once the ice withdraws, how deep are those mix layers? So it's kind of a mix layer story as much as a sea ice. It's interesting. It's a complicated system for sure. But yeah, I look forward to maybe touching base with you on that for sure. Thank you.
Okay, since we are just after the hour, this is probably a good place to finish up. Let me thank Tish, Anna, and Rob again for sharing what are early but already like really exciting results. Really amazing effort there. So thanks so much. Stay tuned for additional information. And again, if you have interest in presenting at one of these seminar series, or you have just thoughts on what would be most useful, please feel free to contact me or Tish. And again, you can find that by looking for the Amundsen Bellingshausen Sector Working Group on SOOS. All right, hope everyone has a great day or a great evening. Take care.
I just want to thank Andy. Thank you for hosting. That was awesome.
All right.
And for the motivation to get this going. We really appreciate that.
Thanks, Tish. Appreciate that.